All right, let's look into this. They're talking about click chemistry. It's very complex, fast, reliable reactions, and it's from catalyzed reactions. Now, this guy got the Nobel Prize for this in 2022. Now, let's see what, well, here, hold on. It's a prime example of copper catalyzed reactions. So copper catalyzes this reaction from these two molecules to form a triazole ring. Well, let's see what these two are and what is this ring. We're going to look at that in a second. But anyway, he got the Nobel Prize for that in 2022 for chemical biology, material science, so forth. Now, let's see what this is, this triazole ring. All right, 5-membered heterocyclic ring containing 3 nitrogen atoms. Well, biology contains a ton of nitrogen. All right, this is what that triazole ring is. It's a 5-membered heterocyclic ring containing 3 nitrogen atoms. There's a ton of nitrogen atoms in all of us. It is a common structural motif found in many organic molecules, including drugs, pesticides, and natural products. It's just a part of the nature of organic material. It contains a lot of nitrogen. And when you have a lot of nitrogen, it grows plants very well. Nitrogen is a plant grower as well. Now, there's 2 different types, they're saying. The 3 nitrogen atoms adjacent to each other, we have to look into that, and the nitrogen atoms not adjacent. Well, I don't care about that. Here's what I care about. Properties: aromatic ring system, polycyclic aromatic hydrocarbons, and a lot of nitrogen. Stable under acidic and basic conditions. They're stable on both sides. However, they can participate in nucleophilic reactions. That's what we want them for. That's what we need them for. That's what he's claimed to have discovered, is that they can do nucleophilic reactions. It can undergo ring opening reactions and can form hydrogen bonds. Polycyclic, aromatic hydrocarbons. Anyway. All right, they're talking about click chemistry and this triazole ring, having all these nitrogens. Now look, here's how this works. This is this triazole ring. All right, it's a pentagon looking thing, 5-sided jobber. Now look at the chemistry here. It doesn't change. This is a 1, 2, 3, this is a 1, 2, 4, this is a 1H, and this is a 4H. The NH, and there's an NH here, and an NH here, and an NH here, they all have one, and then there's 2 N's, and they all have 2 N's. Why are some of them up here, and some of them down here, and some of them over here, and some of them over here? Well, I think I can explain why, and it's because of the interactions they have with other molecules. All right, now, so don't forget now, copper catalyzed, that's the key to this ring, which I just showed you can have a whole bunch of different arrangements. And this is chemical biology. And the reason, well, I think I either showed you or I will show you. I got called away a couple times. Anyway, this is from 2022. They're talking about calling it click chemistry, which I agree. It is click chemistry. It happens instantaneously because of the enzymes. And the enzymes are the things that catalyze the reactions. All right, you see this? These are what they call Feynman diagrams, where they're little arrows and bars and this and that showing positives and negatives and, you know, interaction of what they consider to be the smallest particles, but they're using actually nitrogen and The R means you can put anything in there, basically. But this is all... All right, I think I talked about the different enzymes and the click chemistry and what they break down to. Now, these are diagrams, and Feynman diagrams. Let me show you some of what Yale has to say. Okay, this is Professor Shankar, and he's at Yale, and he is a nice guy. I give him that, and I give him credit for being honest. Now, I just showed you or talked about Feynman and his little diagrams that showed how things bond and so forth. They understood that in the molecular realm, but I don't think they understood it when you go into the isotopes and how these little particles are actually individual little particles. They call them electrons. Well, they are basically, I would call them the gluons, which is the black and the white together. And they do the invasion and all that stuff. But here he's being honest. Now, this goes back 14 years. 14 years ago. Now, this was a quantum physics course, the whole thing, top to bottom. And I actually, not long after this, took a course at University of Geneva, where I showed him my stuff. I couldn't get through to Professor Shankar to show him our light research. So I did take a course at University of Geneva. And I did interact with them, and they did finally agree. What I was talking about was right. Now listen, here's what he has to say.
It's a subject that's kind of hard.
Hold on a second, here it goes.
So this is a very exciting day for me, because today we're going to start quantum mechanics, and that's all we'll do.
Yale course.
Till the end of the term. Now, I got bad news and good news. The bad news is that it's a subject that's kind of hard to follow intuitively, and the good news is that nobody can follow it intuitively. Richard Feynman, one of the big figures in physics, used to say no one understands quantum mechanics. So in some sense the pressure is off for you guys, because I don't get it and you don't get it and Feynman doesn't get it. The point is, here's my goal. Right now, I am the only one who doesn't understand quantum mechanics. In about 7 days, all of you will be unable to understand quantum mechanics. Then you can go back and spread your ignorance everywhere else. That's the only legacy a teacher can want. So,
he's a nice guy. He's just being honest. They're not going to understand it. He just tells them, you say what I tell you to say, and you know, he puts his slant on it, more or less. I didn't watch any, I got to be honest with you, I didn't watch any of it other than I got past this and I said, well, the guy's honest. He doesn't understand it. All right, I showed you all those different transition metals. They all have different charges. Now, the reactions in these nucleophilic reactions can be very fast or not so fast. Now, a very fast one would be this SN2 reaction. You don't have to know all this stuff, but it's a strong nucleophile and a lot of polar stuff, a lot of polarity, very, very fast. And very fast means they're talking about just changing one little thing. Changing from a protic solvent to a polar solvent can increase the reaction rate by a factor of 200,000. I mean, these changes are instantaneous, and that's not even fast. Some of them can take, literally, they claim, this is their claim, not mine, that the change of the chemistry would take up to billions of years in some cases, and it happens in less than 1 second in the human body. That's how fast these catalysts change things, and they are extremely sophisticated, and I mean extremely. You see that? Every one of these little spots in here has a specific, like a key, and there's 20 different codes for all of these little polypeptide chains, these amino acids. There's like 20 of them. I can't imagine how much, and I think they all have to match in order to deal with whatever they're going to deal with, whether it's breaking down a carrot or killing an invader, or breaking into another piece of DNA, or building a piece of bone or muscle or whatever. But they travel through your bloodstream in these little tiny balls, and when they need it, they pop open. And they reside, I think, mostly inside of the cells. All right, the cells that are in your body. But anyway, I think I showed you pretty much what's going on here. These are the transition metals. These are their different charges. And this is how, when they come in and the creature's dead, they have to attach somewhere. And they try to find something that is similar to their polarities. Now let's take this one, number 4, for vanadium. Vanadium can have a whole batch of different charges. But let's see if we can find something in nature that likes vanadium. Well, maybe that does. And why is it a coating like that? Why is it a coating? That's cut in half. That's a Yoan nut. It's an opal, quite obviously. This is a heart. It's a heart. These are the heart valves and tubes. These are the chambers of the heart, and it's just cut right down the middle. Now, this is the ventricle wall. And these are literally the heartstrings. And they come down and they make that heart pump. Now, this is a different chemistry than that. That right there is a tube. And it works itself into the fabric that surrounds the heart. These are valves. You see? And these are all different colored chemistry because it's different transition metals. So there's different biology in here that wants to become stable, but it wants to find the best partner. And in Australia, in this particular area, it had to be completely soaked for literally for a long time, I would think, in basically raw blood and silicates, because there's silicates in here as well. And there's going to be some other stuff in with it. I don't know what it was. I don't know whether it was baked or it was out of the floodwaters quick or something and it didn't have as much boiling time. I don't know. I have no idea. But I do know that Australia is literally like just a big thing of mud, of blood, which is nothing more than red mud. And the redder, the bloodier. And that's from Yoa region, and that's a heart. All right, check this out. I just showed you a heart that was all colored because it's solidified with silicates and blood. Now this is a heart here from a heart attack or a heart, anyway. That's an implant, obviously. This is that blue layer that I was showing you. Now this is also a heart, turned completely to crystal. You see that flap right there? That's one of the attachment spots in this heart that locks it in. They have very strappy stuff. I don't know if you can see that, but that outside layer is, a heart's got to be protected. Anyway, this is this. You see, it's basically exactly the same stuff. In a microscope, it's just exactly the same. And this, I believe, is the bottom of the heart right there. Now, I have another heart that's a crystal one. Now, this one broke right off here. Most of them break right off, and that's what this one did. And this was cut right off of here. So we're looking into this. All right, you follow me? Basically, it was like this. It's, smaller than that. Hold on. All right, so it was like this. And these normally break right across the top, which this did. I can see the valve in there. In a microscope, it's a little more obvious, but you see the different color there. That's basically what you got there. Or it's this side, one or the other. And then I cut it this way, polished it up, and that's what you got, which is this. This up here is the fiber, and that stuff is the real floppy stuff. Now, this one here, hold on, let me get it a little damp. All right, here's what you got here. This is basically that. This wall right here is this. All right, this blood right here is from the aorta coming up through here somewhere. And that right there is the superior vena cava, which is there. And then the aorta is right there. And then there's some other tubing up in here. And that is a crystal heart. And this has the same kind of fabric stuff there. It's got some heavy duty straps here. But that's what it is. Now, that's basically a heart. Well, it is a heart. There's no basic about it. That is the part that goes and it squirts up through these tubing, and that wall separates the used blood from the unused blood. So, and this is not unusual. This isn't no big deal, I don't think. Maybe it is, I don't know. But it's the only one I have like that. Well, I had the other one, I didn't realize it. But it was broken at the top. See, this one here was broken right where they almost always break, right across there. And that's what this one did. It was broken right across here, and that plumbing from the top was gone. This one still has it. It's kind of unusual. So, that's that. Alright, you let me know what you think after seeing this video. They're saying that nucleophilic reactions played long ago a fundamental role in the creation of building blocks and polymers necessary for life during the process of abiogenesis, or the origin of life from non-living matter. So they're saying nucleophilic just happened automatically. That's just not correct in any sense of the word. And they're talking about amino acids, they're talking about nucleobases, and beyond creating simple monomers, nucleophilic reactions are crucial for joining these building blocks into larger polymers like proteins and nucleic acids. They're also, these nucleophilic reactions break down and the digestive things in our body, and they're all basically related to enzymes. I don't think they understand what's going on here. Because these things happen so fast, and if they didn't, you would fall over dead. And these are the products of life. Is bacteria creating? All right, so the bacteria create the ribosomes. Some of them protect you by making you immune. Some of them are spit out down into your digestive system and break down all the foods and stuff that are in you, and break them down and give them over to the protein guys to build stuff up. You can't digest a carrot with no enzymes. Not only that, if you get acute radiation sickness, which means you get pulsed with something so deadly that you get really red sunburn looking stuff, and inside of you the bacteria actually gets wiped out almost completely sometimes. And then within about 2 hours you start getting sick to your stomach and having diarrhea. You're not digesting anything anymore. The bacteria is not there. The enzymes aren't there. You have to have them 24/7. That's why probiotics work pretty fast. And sickness is just the same thing. It works very fast. An enzyme is nothing more than something that's good that's going to protect you and break down foods. And another type of an enzyme is nothing more than something that can hurt you. All right? They both come from bacteria. One bacteria sends out stuff that's made to support your life. The other bacteria has been reprogrammed by a virus of some sort. Some other biology came in there and reprogrammed that bacteria to now create something that's going to harm you, and then it's going to attack your good stuff. So normally it comes out, it creates a ribosome, comes up and it makes here and it says, hey, if you ever see this set of biology again, explode it. And all they have to do is come up and click and it's done. But you have to be able to recognize it, and that's what this does. All right, and the other ones break down your food, so you absolutely need them. But the bad ones take over the program. So what they do is they come in and they go into the nuclear DNA, and somehow they get in here from your good bacteria, I believe. Sometimes a whole new bacteria moves in. But I think they might reprogram some of your own bacteria or our own bacteria and just come in and say, all right, I just changed your ribosome to do something different. And I think they do that automatically in our bodies as we're exposed to new things. Somehow you get immune to it. It's got to be a new program or a new bug that's living in you that's going to deal with that invader or whatever it is. That's evolution. I agree with evolution in that respect, but this didn't just pop out of nowhere. It just all assembled by itself. That's just insanity. Okay, my friends, I don't remember whether I went through this or not. I've got called away on several different occasions here, so I want to update you on this spinning, particles that are in space. What could cause these? And it was a valid question. And what it is the North Star is Polaris. And if you look up at the North Star, the Earth is spinning, and what we're seeing is it's on a tripod, and you're turning it on and off to make these different little flicks. And you can see it's in a circular pattern. That's because the Earth is spinning. All right, so as we spin, and Polaris is up there. And then I believe the statement was, all of them are so perfect. Well, they're not perfect. This person was taking a shot from about like this. That's why these are closer. It's like looking along the shaft here of this here, and these are wider, you see? So you're looking more of it like looking against it. This one you're looking down it, and this one you're looking against it. So it's spinning this way, and this guy's going to be here, so that's how he's going to see it. And as you keep turning on and off, and they call I don't really understand it, so I don't want to pretend I do. But I've been working with a guy, and he's talking about stacking and something else. But I think I got some shots to show you what I know I've shown you. Mason, unbelievable. All right, my friends, we all know we need certain things to eat that are going to be good for us, that are going to help us to survive and make us healthy. And some things are going to make us unhealthy. Now, all right, my friends, I'm just going to make this very simple. We want to become healthy. What we put in our bodies makes us healthy. However, you need the right enzymes, which means you need the right bacteria. And I'm going to be talking about the bacteria that's in our bodies that create these little balls of what they're called ribosomes. They float around, they don't do anything until they're called upon, and they create absolutely stunning chemistry. Now, let's get started, because I say everything is biology, and I stand behind the things that I'm showing, and I show evidence to support the claims I make, and I actually use other people's claims too, like Fermilab, to show the same particles. If we can understand how to work with those two particles, which I do, it's going to make a huge difference in how we treat everything. Because these are the building blocks of life, those two particles, and together they make what they call a gluon. And I have all this stuff on dipole electron flood theory, right here. These are the two particles together. They know this, and they've seen these, but they see them when they crash huge things together and get all kinds of debris. I am going to explain this, I hope, well enough for you to understand. But these are gluons, which they're actually heat. They're heat. They're not electricity. Electricity is just the white part. That's electricity all by itself, wanting to get back to that black part desperately. Desperately. That's electricity. All right? That's what gravity is. And everything that's made is made like this, of those two particles together. And when you get to the molecular size, which is the next bit of stability above photons. Photons appear to be stable, and they're like two bar magnets back to back. And then after that, you don't really get a lot of stability. So here's a photon back to back. All right, and if you go to here, that's radioactive. That'll hurt you. Too many particles all at one time. So if you're here, the ones we work with, the light particles, they're not going to hurt you because we're in that realm. But once you get above that, these particles are not stable and they're too big. That's why they're called radioactive. They're going to fall apart or bond with something and that sort of thing. All right, dipole electron flood theory solves every single issue they've had, including the dark matter, why we've never even seen it, because it's always inside of the white matter, until we saw it through our experiments, and it's quite obvious. I mean, they've seen it, they didn't realize what they saw. The dark matter obstructs the light from behind it. That's the only reason they could see it. They say it always has a glowy edge around it. And that depends on the color of the particle. Like the green has a green glowy edge around it. But you can see them, see? But there's green behind it, so it can't hit you. So it's in its way. And the same thing happens with the red. You see? That's the black, and it's got the glowy edge. There it is right there. And the other one is just glowy, and it has no mass. I can't explain that, but I have to agree, I can't see it. But there is the black one, sits on top, so it obstructs your vision. You're not seeing it, you're seeing not what's behind it, which was the white, or the green, or red in this case. Now, what's down here, this is what they want to see, is fission and fusion. Fission means the muon comes away from the electron showers, just what we did. The black one is the muon, and the only reason you can see it is sitting on top of the white, see? They're all over up in here, the black ones, you just can't see them. They're part of the white. The white is the part that you can see. The black just is unseeable until you do what we did, which separates the black from the white. Otherwise, it would always be like this. And all you would see is this. Because they're just unseeable. They see them because they're obstructing some form of light that's supposed to be coming. They can see them. They know they're the tiniest thing. That's from Fermilab. That's from Fermilab's article. All right, so I'm not making this up. Here it is, actually, here it is right here. It's from 2013. Fermilab, that's their article. And it says exactly what I said, how they work and everything else. We started with light. They started with this. So they were digging through debris. And they're still doing it now. So That's just the universe we live in, which is space is not empty. Empty space isn't empty. That's the same guy, Don Lincoln. This is the same time. February 2013. He's, and I did contact him, and we went back and forth. And did not end well, so that's just the way life is. I think I presented my case, and I think I've shown the particles that are the photons. And these are not quite photons yet. You see them, they're flat like this, and then they go like this. They always seem to work with the polarity of the Earth. So they're not like this or that. They're always straight up and down or flat. You see it? All of these are particles moving this way, interacting with this field that's being created by the concussion of these particles. That's what this is a reverse electromagnetic field. All right? And it's pushing back against these particles and flattening them. For some reason, I can't account for that. I don't know why. And their fields show up in the other part. I'll show you the waves. But these turn into the beam because they're hitting direct on here. And here it is again. You see? That's the wave coming across, and then all of a sudden it says, hey, we got to get going. The Venturi says, it just sucks the particle like a rocket ship. And it bangs at the Venturi, it can't get through. So all you come through is the white. Here's this interaction right here. Don't forget this. Look at how white those are. That's because it's pushing back against them. And anytime you have push to shove, you get white. All right? You push and I shove back, we get white. You push harder than me, I shove back, I get less light, you get more light. All right? And that's what this whole thing is about, is accelerating the light. Here is light that's just beginning to accelerate. But you see all those little white particles? Those are little tiny glows from the gases that are in the air as this begins to push against it. And again, this one gets brighter because it's got to push harder to get these things out of the way. And these don't push back a lot, so they just sort of push away. And then it starts to accelerate really pretty good. And right here, it feels like it just hit a wall. And that's because this is pushing back so hard that this thinks it hits something solid, basically, right here. And so it shows as a photon. Otherwise, I don't think you see them. I don't think you can see them until they really hit something hard. And that's why they see them at CERN and Fermilab and all the rest of them, because they hit something really, really hard. Now, we hit it really, really hard because of the bounce back. And it bounces back really hard. And again, these are the Higgs fields that come out as it shoots through here. Looking into it, we can see the Higgs fields. And those are the particles, the blue and so forth.